Okay, let's get going. So today's February 25th. We've got, I think it's an interesting class today. We've got a number of things we're going to do. I'm going to do a little Unix tip of the day. I might do that kind of when we go through some demonstrations later. In fact, I've actually shown you this tip before. It's the time program that allows you to time your program's outputs. And we will see how that works. I'm going to go through some Homework 3 clarifications. Right now, there's actually one problem outstanding with my test code. It doesn't seem to be producing the output that it should. Thanks to Alex King, who was in the warning class today, who's actually mostly done with the assignment. He emailed me, or he put something on Piazza that said, hey, your code's not matching mine, and I think I'm right. and I said, you probably are. And in fact, he was. So as it turns out, and it was, I don't know why I missed the problems. But anyway, my program wasn't handling a pointer correctly, and there's something else that I have yet to figure out, but I only had 5 minutes to look at it. So don't try to do test B tonight. Or no, not well, until like maybe 6 p.m. tonight when I fix it. And I'll figure that out. But anyway, I'll talk about some other homework clarifications. Then we're going to do a little bit of a math review. Today is a little bit more math heavy than some other days. So those of you who've been waiting around for like, when does computer science get mathy, which it kind of does in some places, today's the day. Those of you who, there's one slide where those of you who are not math types need to like shield your eyes a little bit because it's a little bit way too mathy. But it should make the other ones happy. So I'm trying to make everybody happy. Anyway, and then we'll go into this thing called big O notation, otherwise known as asymptotic notation, or the way we analyze programs to compare them and to talk about how an algorithm will actually run given bigger and bigger inputs. Okay? Questions before I go? Begin? All right. Let's first talk about homework 3. So there have been a couple issues with homework 3. One of the problems with writing assignments for this type of class is like I don't get to actually check my output with anybody, right? I'm supposed to know this stuff, but sometimes I get things mixed up. So a couple things I got mixed up with were the some of the I actually tested it thinking I tested it on the homework machine. I didn't, so there were some includes and things that needed to be changed, and a couple of syntax things that needed to be changed. It's all been changed in the files that are currently out right now, except for the testing ones, but the actual files are good. But if you have questions about what the issue is, or if you've got some questions and your first line of defense is to go to Piazza and see if anybody else has the same questions. Second line of defense is to actually put a post on there and say, hey, Chris, you're probably wrong about this, which is the way it goes. One of the other issues is people have been questioning whether or not some of the times are going in correctly. Keep in mind that if you look at the files that are input files to the actual program, they are what Google would put out, and Google actually uses GMT time, which is Greenwich Mean Time, which is 5 hours in the future from us. And so I do a conversion when I import the files to actually change that. So if you look through the actual imported files, you'll notice that the times are 5 hours off what your program is hopefully outputting. And that's correct. OK? So don't worry about that. It's handled already. Hopefully I handled that properly. Any questions so far on the homeworks? Anything you don't understand? Yeah.
Do we need to download anything again?
Yeah. So when I fix this other thing tonight, which I will, then I will put a note saying recopy just the test files. And I'll show you how to do that without copying everything else if you've already done work. And it'll be a zip file as well. So it should be not a big deal. But if you've been working on it, and if you have gotten to the stage where your tests don't agree with our tests or the tests that I gave you, well, again, you're probably right, not me. So give it another few hours, and then it'll be up there. So sorry about that. Any other comments or questions about the homework? Yeah, Allison.
Is it okay if we change some of the code that's already written? Like, so in the print out function, the first one we're supposed to write, I just like changed the little.
Yeah, that's fine. If you want to change something that's already written, that's fine. Don't change what it does. I mean, that's the only thing. If the output is supposed to be a certain output, don't change that. But you can modify it if you want. If you come up with a better way to do it, let me know. I mean, you might. I'm not saying you won't, but if you do, certainly let me know and say, hey, I could have done this better than what you did. And I'll be like, great, you win. Alex King wins the better than the professor student of the day for today. So anyway, anything else? Yes, Naomi.
Kind of going off of that, one of the requirements is that we change the print out function to use like the convert 24 hours, but your print function already does that. So
Yeah, good question. So Naomi says, hey, the output, you need to change, it says you need to change the print out function. I think I already did that for you. So that may have already been done. And if it was, I just forgot to take that out of the description of what you have to do. I didn't want you to do too much.
yeah, I know.
Yeah, cool. Anything else? All right. Cool. All right. Well, let's get going on. Let's actually start with a little bit of a math review. Okay. Again, those of you who are not math types, don't stress about this too much. I just wanted to, you've all seen this beginning stuff before, although I doubt any of you, well, some of you may have taken discrete math already, but if you haven't, that will be upcoming in your computer science career if you're a computer scientist. If you are not, you don't need to worry about it. But there's a couple little things I just wanted to get out of the way so that we're on the same page when we talk about some of the math that's involved with this notation. So the first thing, so we've got this summation symbol, and all that means is a sum. And if you're summing some function I, and you're going from I equals a all the way to b, well, you're first going to do the function of a. And then you're going to do the function of a plus 1, and then function of a plus 2, because this counts up by 1. Easy enough, and you go all the way to the function of b. Any questions on that? Pretty straightforward stuff. Okay. We use the summation functions a lot in this form in loops, because loops in general are integer loops, and so you increase your integer by 1, and then you do the next iteration through. So if we're counting the number of loops we do, or the amount of time it takes for loops to run, well, we need to do some form of summation. And the summation is going to be one after the other, counting up by 1. So that's where we end up with this sort of thing coming up in computer science. OK, we've also got these things called a geometric summation. And a geometric summation says if you've got n from greater than 0, greater than or equal to 0, and a being between 0 and infinity except for 1, just doesn't work with 1. We'll see why in 1 second. Then you do this summation, and it's a to the I, just taking the summation of the exponents of a, right? A to the I, a to the 0 is 1, a to the 1, a to the 2, a to the 3, all the way up to a to the n. If you do all this out, OK, and it just goes, if it stops at n, this is what it actually ends up at. 1 minus a to the n plus 1 over 1 minus a. Kind of a nice little closed form of this whole summation here. Kind of neat. Okay. If you happen to have a less than 1, then if you go all the way to infinity, that actually turns into this. The sum of a to the I from 0 to infinity, if a is less than 0, it actually converges to 1 over 1 minus a, which is also kind of a neat answer here. Okay? So that's the two summations that are called geometric summations. Okay? All right. Computer scientists use the following geometric summation pretty frequently. Okay? If you use, and you should kind of know what it means, and we'll go over it a little in a couple minutes. If you go from 0 to n minus 1, and you're doing 2 to the I, and 2 is a very important number for computer scientists because because binary is binary is based on 2, and this sum here, if you do it all out and you go n minus 1, you end up with 1 minus 2 to the n minus 1 over the quantity 1 minus 2, which is negative 1, and this ends up being 1 minus 2 to the n minus 1, which is just 2 to the n minus 1. It just kind of flips the top up here, and that's what it is. Now, in computer science, why do we think this is important? Well, if you have n bits, in other words, places in memory that can hold either a 1 or a 0, okay, the largest integer that you can hold in that representation is 2 to the n minus 1, which is kind of cool. Okay, if you've heard that you have a 32 or a 64-bit integer in your computer, you have a 32 or 64-bit computer, well, you can hold 2 to the 32 minus 1 or 2 to the 64 minus 1 numbers in one location, So the last class, people didn't know how to count in binary. Have people not counted in binary before? Some people have. Anybody not counted in binary? That's OK if you have not. Let me quickly show you how to count in binary. And you don't have to memorize this right now, but it's very easy to do, although numbers get big very quickly, as you might imagine, because you've only got 2 digits. When you're counting from in base 10, okay, if you're counting in base 10, you start at 0. Let's say you start at 0, and you count up until you run out of digits to count. And the digits are just 0 through 9. Okay, when you get to 10, what do? You do 0 through 9. You go 0, 1, 2, 3, all the way down to 9. When you get to 9, you've run out of digits. Okay, what do? Well, you have one more decimal place that you or well, I guess it's the other way around. You have one more tens place. And what happens is 9, you get a 10 for a 1, and then you get 0, and then you start counting up again. OK, this is not rocket science. You guys have been doing this since like nursery school, right? You count up like this. Binary is exactly the same, except you only now have 2 digits you can work with, 0 and 1. So here's what you do. You start with 0. And then you count up 1. And you go 1. I can do that. We've run out of digits. Just like we run out of digits going from 9 to 10, we've run out of digits going from 0 to 1 to whatever next comes next, which happens to be 2. But in binary, we have to get another 1 and do 0. So this is 0, this is 1, this is 2. OK? Well, can we count from 10 to 1 more than 10 using the numbers that we have, 0 or 1? Sure we can. So we go 1, 1. And that's 3. Now we've run into a problem again. This is analogous to hitting 99, where you've hit 99 and you've run out of digits again. OK? So what happens? You put another 1, and you start over from 0. OK? So 4 happens to be 1, 0, 0. And then 5 is 1, 0, 1, and 6 is 1. Well, same thing here. When we go from 1 to we go to 1, 0, 6 is 1, 1, 0, and 7 is 1, 1, 1. OK. Given 3 bits of information, we can go all the way from 0 up to 7, which happens to be 2 to the 3, which is 8, minus 1, which is what we're talking about up here. OK? Any questions on counting up? I mean, you can practice this, and it gets a little, like it sometimes gets a little confusing. But it's just a pattern, just like you've learned in decimal math. It's just a different pattern because you only have 2 digits. And that's why numbers get really long really fast, because you got to keep adding another 2's place every time you get 2 more up. So, well, every time you get another power of 2 up, just like in 10. Questions on that? OK, good. All right, so let's go on a little bit more. There's a geometric series that looks like or summation that looks like this, OK, which is if you just have I, if your function is just I, and you're counting from I to n, well, this is just all the numbers, 1, 2, 3, all the way up to n. And there's an interesting apocryphal story about Carl Gauss, who is one of the who's like one of the most brilliant mathematicians ever. When he was in grade school, this is again all apocryphal. When he was in grade school, his teacher supposedly was trying to keep her kids busy, and he said, "Go ahead and count. I want you to sit there and count the number or count the sum from 1 to 100." Right? And like 2 seconds later, Gauss raises his hand and says, "It's 5,050." Right? And she goes, "What are you talking about? And how'd you know that so fast?" Well, it turns out he did this little calculation in his head where he said, if I'm going from 1 all the way up to 100, right, 2 and 99, right? If you look at 1 and 99, they add up to 100, and 2 and 98 adds up to 100, and 3 and 97, and it's just kind of, and he had this figured out in his head, which is exactly what is up here. OK, so anyway, that's another kind of geometric summation that is an interesting one anyway. Questions so far on those? No, good. All like algebra math. OK, then we get into logarithms. Now, we've mentioned logarithms a number of times in class here, but I've kind of hand-waved around a little bit. Today, we're going to go a little, well, at the end of class, we'll get a little bit more into detail about logarithms. But this is how we represent a logarithm, obviously. Log b of a equals c. And in computer science, what we say, we omit the base when we're talking about a base of 2. Why? Because we like 2, and we use it a lot more than some of the other bases, right? So, in calculus class, you use base e all the time, right? But in computer science, we use base 2 all the time. And so what that means, of course, is the log of, say, 1024 is 10 because 2 raised to the 10th power is 1024. OK? So logarithms. We will talk more about why logs are important in a few minutes. OK? And again, logarithms get big slowly, which is great for computer scientists. OK? Questions on the math part? All right. So let's start talking about algorithm analysis just a little bit to start out here. We're going to start looking at algorithms and data structures, and we're going to start trying to figure out how they change as the input gets larger and larger and larger. OK? Why is that important? Because if you have an algorithm and you want to stick lots of data in there, and that's really what goes on a lot of times, you have these data structures, and you try to cram as much in there as you can, problems get bigger and require you to store more things. OK? We could, or we have to actually take a look at these. So let's take a look at this one first. OK? How do you actually go about analyzing programs like this one? So before we go into the details, let's just get our head wrapped around what this program does. It's not too hard, I don't think. OK? It's called array max. What I do is I'm passing in an array. I'm also passing in the length of the array because it's easier than trying to figure out where it ends there, right? So I'm passing in the array and the length of the array. And then the first thing I'm doing is I'm setting the current max, some integer, equal to the first integer in the array. Then I'm going through a loop, and I'm starting the loop at 1, not 0, because I've already done the first one. I've already got that in current max. And then I'm going all the way until I is less than n, and I am incrementing I as we go along. And then in the loop itself, we say, look, if the current maximum is less than the number that is next in the array, then we have to set that to be our current maximum. And then at the end, we return the current maximum. We do that n minus 1 times and blah, blah, blah. OK. Questions on what the program is doing up here? It's just finding the maximum value in a list. So far, so good? All right. How might we go about analyzing this? Like, what are some ideas that we might have that you might have to go ahead and figure out how fast this runs if we know that we're given n numbers in this array? Ideas? What's kind of some of the things we might want to do or we might think about doing? Maybe I didn't set it up right. If we want to analyze this program, how are you going to tell me how fast it runs? Yeah?
Let's say every time you go through a number in an array, it takes 1 second. So it takes n seconds to go through n number.
Ah, OK. So the answer was, OK, so skip all this other stuff and go through the numbers and say, look, it goes through n times. Actually, it goes through this loop n minus 1 times, actually. And then say, well, if it takes 1 second, then we have to figure out what it means if we have twice as many or 3 times as many or something like that. That's not a bad idea. Allison, you have another one? That was the same sort of thing? OK. OK, but let me ask you a question. Does it take some time to do this line of code? Yeah, it does. So let's not ignore that quite yet. We may eventually, but let's not ignore that quite yet. So we might need to take some time to do that. Does it take time to set I equal to 1 to begin with? Ah, sure it does. Does it take time to compare I to n? Yeah. Does it take time to return the result? Yeah, it does. So there's lots more details to this than just kind of hand-waving around it. Let's talk about how we might do that. We could take this program. We've got it in C++. We could compile it. And what we could do is we could actually go into the code that gets compiled. And we could start looking at the actual machine code that's actually executing this instruction. Right? I went ahead and, oops, uh-oh. I went ahead and, hopefully my computer's not crashing. Oh, I went ahead and got this. I took that program, and let's see, where did it go here? There it is. OK, I took the program, and I threw it into the disassembler. And this is what it looks like. And it's kind of ugly. And the test on the midterm will cover all of this. I'm just kidding. This is not coverable. This is all like assembly language stuff, right? And what's nice about the way you can do this, you can actually have the compiler tell you where in your regular C++ program these lines are. So like this location right here is line 13 in your C++. And look what's happening. Oh boy, okay, so there's something being pushed. Hey, look, a machine instruction is push. Oh, that's interesting. Push is a really low-level thing. Okay, and then we got some offsets here. And then the thing about machine code is, so you guys get all upset about C++. And you're like, oh, the syntax is hard, and I don't understand it, and right? Well, you end up looking at machine code, and your eyes start bleeding, right? And this is not necessarily like. The interesting part about it is there's a lot less, like there's so much fewer that can happen in an assembly language program. But the problem is you have to do everything, right? Like you want to set I equal to 1. Well, first of all, you have to define the location, right? And then take a register value here, and you have to actually move something into that register value, and that's just to like, and that's just a set of value, right? Not to mention looping and all this other stuff. You have to do everything yourself. Okay, so it gets kind of ugly, and you don't really want to do that, right? You don't really want to have to do that for this program, all right? And go and find out every little step. Now you could, but you don't want to. Now there's other issues too, right? The other issues, for instance, are if you wanted to figure out what the computer itself was doing with this, well, sometimes, like for instance, if you go back here, whoops, let's see, where were we? If we go back here, and how many actual machine instructions do you think this takes? Well, not machine instructions. Let's actually go one level higher. How many different things does this line do right here? How many different things does it do? Int current max equals a 0. Anybody want to guess? Yeah. 3. What are the 3 things? Create a new integer. Dereference the array, yep, and then set it equal there. Yeah, that's 3 different things. In fact, we're probably going to ignore the fact that it has to create it right here. The nice thing about the way this is written is that the compiler generally does it before the program starts. It knows what's going to happen there. Now, well, kind of. It does have to. There is some overhead to involve it. But yeah, you can either say 2 or 3 for that. Now, one problem with this is we don't even know where in memory that is. Like, in other words, there's different parts of your memory system, right? We talked about this a little bit before. I mentioned caches before. There's actually a lot of different levels to your memory system. If you have your fancy computer, right, and you look at the different types of memory that the computer has access to directly, okay? In the bottommost, like the lowest level on chip, there are these things called registers, which I just kind of showed you up there. There's these things called registers, and registers are really, really fast, and they're used all the time, and they're super expensive to design because they're actually on the chip as like hardware structures on the chip itself that do this really fast like input-output sort of thing. And your computer might only have 32 of them or 16 of them or maybe 64 of them, depending on what kind of computer you are, but they're really fast. The next level of memory would be, say, your cache. And your cache, we talked about earlier, was another fast piece of memory. Caches are really fast, but they're not as fast as registers. Why? Because it costs too much to make registers like that, and there's not enough space on the actual die to do it, the computer chip to do it. But they're fast. Then you've got your main memory, right? And that's also really fast, but slower than the other two. And that's, you can get gigabytes of main memory now. And then what's the other level, the next level of memory that you can have? Any ideas? Nope, not RAM. This is your RAM. Virtual memory, where's your virtual memory located? There you go, on the hard drive. So if you run out of memory in your main memory, your computer is actually smart enough to go and put some of that main memory temporarily on the hard drive, right? Problem with that is, let's say your array is in that memory and ends up on the hard drive. Your timing is now a little bit off. Okay, there's an analogy I was giving somebody the other day. There's a good analogy of the difference between registers all the way up to the hard drive. Let's pretend that if you want to put something in a register, it's as if you had a pencil that you wanted to take off your desk and write something down with on a piece of paper, right? That's what a register is. You're sitting at your desk, you have a pencil, you grab the pencil, you write down on the piece of paper, and that's a register. That's how fast a register is, okay? Cache is as if you had to get up out of your desk because the pencil was like on the other side of the room, or maybe the other side of the house even, but on the other side of the room, right? So you have to get up out of your seat, you have to walk over to the other side of the room, grab the pencil, walk back to your desk, sit down, and then write that. That's how long it takes cache to work, proportionally. Main memory is as if you had you didn't have any pencils in your house, but your neighbor had a pencil, right? So you have to go out, get your boots on and your coat on, and you make sure the dog's tied up, and you walk out the door, and you go down the street a little bit, and you knock on your neighbor and say, hey, can I have a pencil? And he gives you the pencil, and you walk back, and then you write it down, right? That takes a certain amount of time. Any idea how long it takes to do disk access comparatively?
You have to import the pencil.
You have to import the pencil from a foreign country. You know what? You're actually not too far off, right? The analogy that I've heard is actually, it's not that your pencil at your neighbor's house, it's that your pencil is in California and you have to drive there and pick it up. That's how long it takes, right? Comparatively. You have to get in your car and be like, oh, there's a pencil in California, 4 days later, you're back with your pencil. That's how much longer it takes. So if you end up with something like this, so trying to figure out the memory access, you don't want to worry about that stuff if we can help it, okay, obviously. But that also means that if you end up in a situation where you've got a data structure that does have to write to disk, all bets are off on all this analysis we're going to do. Because the minute it writes to disk, it's like going to California, right? You're not trying to, it's like, oh, how fast are you in the 100-meter dash? Oh, you're 10 seconds or 15 seconds or whatever, right? Well, I mean, if you all of a sudden have to drive to California in the middle of your race, then then you're going to be off a little bit, right? Okay. So anyway, we've got the program here. Here we could do all that assembly language business and trying to account for the fact that computers do weird things in storing memory and all that. We don't really need to do that. We could do all that and calculate it all out, but it would be a little bit intense, as you can imagine. Okay. Instead, okay, what we're going to do instead, we already covered this already. Instead, what we're going to do is we're going to actually define some primitive operations, and we're going to just say if that operation happens, then we're going to count that as 1. Kind of like what you're saying up here, that you can actually just count it as 1, and we will actually be able to deal with that. Okay, here's the functions. You do not need to write all these down. Okay, but these are the primitive functions that we were talking about. Number 1, assign a value to a variable. Okay, that takes 1 time, let's say. 1 time step, whatever. Calling a function. Well, we know that doesn't take 1, right? We know there's lots of little things that go on. You have to store all the pointers and all the memory that you're using and all that. But we're going to just call it 1. It's just easier that way. Arithmetic, adding 2 numbers, takes 1 step. Also not necessarily true when you compare doing addition and multiplication, right? Much different amounts of time, although computers are pretty good about doing multiplication these days. Comparing 2 numbers, is one number bigger or smaller or equal to another number? That takes 1 step. Indexing into an array, same business, takes 1 step. Or following a pointer to some location, takes one time step. Returning from a function, same deal. We know that actually takes longer, but we're just going to call it 1. Just going to call it 1. Okay? Let's do that kind of analysis on our program. We're not going to get into the assembly language stuff. We're just going to look at the types of operations here. And good point earlier. For this analysis, we're going to ignore the fact that this integer gets created in here. Okay? So let's take a look at this. When you get into the function, the first thing you do is this. And again, you're creating an integer, but we're not worrying about that. You are setting the value from A0 into current max. Well, that's really 2 primitive operations, right? Because you've got to dereference A from the array, and then you've got to set it into there. 2 operations. Then you're going to come down here, and this loop, there's a reason C++, the people who designed C, made these kind of loops this way. Because you get a lot out of them. All right? There's actually more to this loop than you might think. Right? There's a lot going on in this one statement. Why? Because it's taking a while loop, and it's saying, let's make it kind of cool where we know how many times we have to go through it. Right? Well, what do we do first? First thing we do, we set I equal to 1. That takes 1 operation. Then we check if I is less than n. How many times do we do that? We actually go through this loop n minus 1 times, meaning we have to do that check n times. Okay? Think through that if that doesn't make sense. We go through the loop n minus 1 times. The last time through, or the last time we check this, it turns out to be false, and we skip the rest of this and go down to the last line. So there's n times through this loop, or the n times, n minus 1 times through the loop, n times this thing gets run. Questions on that? OK. And then this actually happens at the end. Remember, that happens after you get done. Then you increment I. Right? So you increment I after there. And I gets incremented n minus 1 times, because the last time it's already checked and seen that we're a false condition. We do not increment I again. And so that actually only happens n minus 1 times. But even though I++ is the shortest thing you can write in C, two things are happening here, right? You've got I being incremented, and then the value of that increment is set back into I. Two operations. OK? So how many times do that? Do 2 times n minus 1 operations. That's how many times this happens. OK, so far, things are pretty straightforward. Now we get into the loop. If we look at this line, if current max is less than, there's two operations going on here, right? Same thing. You're doing a comparison, and you have to dereference this AI again. All right? There's a reason sometimes people have another temporary variable to keep these around, because if you keep dereferencing this, it takes a little time. Why not keep it around? It takes less time to do than that. But you don't have to do it that way. Anyway, so there's two things going on here. OK? And that happens how many times? How many times does this line happen in this program? N minus 1, because it goes through the loop n minus 1 times. So there's 2 times n minus 1 operations. OK. The next line is where it starts to get a little crazy. Right? Current max equals AI, meaning we're just setting current max equal to the value if it turns out that the value was less than the value in the thing. Oh, no, my pointer's dying. Here we go again. I'll have to grab the stick. So in this case, how many times does current max A equals AI happen? We don't really know, because it depends on what's in the array. OK, you don't actually know. Why? Because it could be that the first value in your list is the maximum. And then you never have to do this again. You never have to do this part again. Right? You do it once. Or it could be that your maximum is the last value. Right? And it's increasing as you go, so that every time you check current max versus what's in the array at that location, it's always less. And so you have to do this every time. We can't figure out the exact amount, but can we figure out a range? Yeah, Dylan?
Yeah, we can set an upper bound. Right?
We can set an upper bound, and we can also set a lower bound. We certainly can. We can say that it happens 0 times, right? Or, yeah, it never has to happen. Or we can say that it happens n minus 1 times, and then 2 operations, right? So at most n minus 1 times, and at least 0 times. It never has to happen. So there's a bounds thing we've got to talk about. Then when we get into this stuff, we have to talk about bounds a lot of times. OK, then it goes through a little. Yeah, Allison.
So just to go back to something you mentioned, so if we wanted to make it quicker, we would say we could just set like before the loop A, or inside the loop before the if statement A, at the I address.
Dead too.
Or it's like some variable.
Yeah, you could, if you wanted to, you might be able to speed this up. In this case, you're not going to speed it up much, because you've got to dereference it, and if you do it twice in a row, it's not going to be much difference. But if you were able to, or if you had lots of times you were using AI in this function, just put it into a temporary variable at the beginning. Then you don't have to dereference it every time. It saves time. Saves time, yeah. OK, so then finally, we're done with the loop. Then we get down to this return current max, and that takes one operation, we're going to say. OK? But we loop a total of between 4 times n minus 1 and 6 times n minus 1. And if you figure that out, it's going to be 2 times n minus 1. Let's see, the loop total, that's including the stuff up here. 4 times n minus 1 by 6 times n minus 1. OK? Questions on that? All right, let's add all this up. We're going to take all those numbers and add them all up. This is what it looks like. OK? You add up the 2 from the initial setting current max equal to the array and dereferencing the array. Then you add 1 for setting I equal to 1. Then you set n. You add n because that's how many times through the loop it goes, et cetera, right? And you add all these up. In the least case, you've got 5n operations here, right? You've got 5n operations. Not even my pointer's not even working. you've got 5n operations. And at most, you've got 7n minus 2 operations. Okay, not a particularly fun number to work with, but it's all right. We could call this instead a best case scenario and a worst case scenario. If the maximum happened to be right at the beginning, we would never have to do it again, the best case. The worst case is the maximum is at the end, and every value in between is greater than the maximum, the current maximum. Okay? Can we do an average case? The average case is actually pretty tricky to do. Not necessarily for this one, but in general, average cases are hard to do. Okay? There are, most of the time, which one do you think we care about? Worst case, yeah. We don't care about the best case necessarily. I mean, if it happens that it gets our best case every time, great. We do care about the average case, but really we care about the worst case. Because in the worst case, that's how you're really going to slow down your program if you end up with some data that just is not in the form that makes your algorithm work very well. And you want to kind of figure out where that point is. There are certain cases where average case makes a difference. Later in the class, we'll look at an algorithm called the quicksort algorithm, which is a sorting algorithm that has a worst case that's pretty bad, right? But the average case, somebody else figured out what the average case is. The average case is really good. In fact, it's the best you can do as far as sorting goes. So in general, it's actually a really good sort. So even though it's got a really bad worst case, it's generally very good. So most of the time, we won't have to worry about the average case. Sometimes we will, and I won't make you figure that out. I'll just kind of say, hey, this has an average case of blah, blah, blah. Questions on that? OK, good. So let's look at the summary here. First of all, do we need that much detail? No, we don't. OK, I mean, just like you guys were saying at the beginning, we don't need that much detail to get a big picture of this, overview of this. What we're going to want to do is get what we call a 50,000-foot view, right? Where we're kind of looking at the holistic algorithm and trying to figure out, hey, can I make a big comparison versus about how what the behavior is? In the case of the array max function, that big picture approach says, hey, look, if you have the algorithm's time actually grows proportionately to that n. In fact, what we call linearly to that. So if you have 10 times more integers, right, that you're looking through, well, your algorithm's going to be 10 times worse or longer in the worst case. Okay, that's the kind of analysis we want to do. Okay, but we need to formalize this just a little bit. Okay, we need to formalize it in the following sense. We are going to come up with this methodology called big O notation. You can think of the O as standing for like on the order of. Okay, technically it's actually, I think it's a Greek omega is what it is, or maybe it's an omicron or one of those Greek letters, right? But anyway, it's the big O notation is what we're going to use to give these big picture overviews. Okay, now brace yourself. The next slide is the one that I said was the mathy one. So shield your eyes if you don't like math. Take a look at this, though. OK? This is for you math folks. OK? Here's what big O notation really is. OK? Let f and n and g and n be functions. They're mapping non-negative integers to real numbers. We say that some function f of n is O, or big O, or order of g of n if there's a real constant, c greater than 0, and an integer n not greater than or equal to 1, such that the function itself, f of n, is less than or equal to that constant times the function g of n, okay, for every integer above that. Now, let me distill this a little bit so you don't have to worry about the math parts. Take a look at these two functions here. Okay? At some point along these functions, there is a point where this function is always and forevermore less than the one above it. Do you see how that works? What's going on is this one happens to be higher at the beginning, right? This one does. G of n is higher at the beginning. We'll go this way. Higher at the beginning, and then it suddenly drops down. Sorry, G of n is lower at the beginning. That's what I meant. G of n is lower at the beginning. It ends up going above and never gets below the function again. Why do we need to be this pedantic about it? Well, it turns out that some algorithms have a certain startup cost. Okay, that means that they will do poorer or less well They will be slower than other algorithms that are technically, in the long run, slower. Okay? So you just have to account for that little startup cost, right? And once you account for that startup cost, once you figure out that, OK, at some point here, the startup cost is not going to matter anymore. F of n is always going to be less than g of n. That's the value of the function that we're going to use for big O notation. Okay, we're going to say that the function f of n is big O g of n because it's always going to be less than g of n after some amount of time. Okay, that's the mathy part. Don't be scared if you're like, hate the mathy part. Okay, and if you love it, great. Here's how we're going to look at the 7n minus 2 part of the max array. Array max, rather. The dirty little trick to this is the following. You look at all those steps that you calculated, and we don't necessarily need to go into the detail to do that. I just wanted to show you that you can do all that detail if you need to. You go and you look at that detail and you say, throw out all the constants. Just throw them out. 7 is going to be gone. 2 is going to be gone. Okay? And the pedantic people in here might go, wait a minute. What you're telling me is, you're going to tell me that some operation depends on the number of elements. When really, in this case, if I add 10 more elements, it's actually going to be 70 times slower instead of 10 times slower. Or if I had 100 more elements, it's going to be 700 times slower instead of 100 times slower. Right? Yes, I'm telling you that. Right? But we don't care about that. We don't care about the fact that it's 70 versus 100. We're just going to not worry about that. We're just going to worry about the fact that it's going to be, I should say, sorry, it's going to be, yeah, it's going to be 70 versus, we're just not going to worry about that and throw that away. We're going to throw away the 2. This little 2, remember where that came from? That came from like calling the function or returning the function. It came from setting I equal to 0. It came from setting that first maximum business. Those like little one-offs, we're not going to worry about that. If you've got a billion integers in that list of yours, does it matter that one time operation is spent setting the initial values? Doesn't matter at all. And that's what we're thinking. We're thinking big, like long-term asymptotic behavior. In other words, behavior that goes on for when we have lots and lots of values, as it grows, as it grows. Okay? So we say that something that shows that actually has 7n minus 2 as the function for the number of operations it does is just big O of n, because it's on the order of, you multiply the number of inputs by 10, you get 10 times the speed decrease. See what I mean? That's all big O is really about. It does take a little while to get your head wrapped around it. So don't stress about that. I mean, if this is the first time you've ever seen this, no worries. Okay? But let's go through a couple other like examples of the types of big O notation. These are the ones that we're going to focus on. Okay? We're going to focus on these ones. And in fact, most of them, the last two, we're not going to see too often. Okay? But the first one, this is like the holy grail of computer science. If you can get some algorithm that has n number of elements, and you can apply some function to that element to do something involving that algorithm or data structure, and it doesn't depend on the number of elements, we say that it's constant time, which means it takes one operation to do it, and then you don't need to do any loops, and you don't need to go through all the elements, and blah, blah, blah. Have we seen anything in this class so far where we take constant time to do something? Yeah? Accessing in an array, absolutely. Okay, if you want to insert into an array or access something from an array, if you know the index, do you have to go through all the elements to get there? No, you don't. So perfect. You just grab the index right there, or you grab the array, the value straight from that index, and you're good. And that's a constant time operation. Awesome. That's why we say arrays in general are very fast. Now, if you get to a point where you're inserting and you have to expand the array, well, all right, now all bets are off, and you've got to do more analysis. But we just generally kind of sweep that aside for this kind of analysis. We don't worry about like, oh, I have to expand the array. Not too much worry about that, especially when we expand the array smartly, like doubling every time. You don't have to do it that often if you do that. OK, that's what constant time is. Logarithmic time. Now, we have mentioned this a number of times in terms of the tree structures. OK, tree structures are naturally logarithmic because the height of a tree is the log of the number of values in the tree. So a lot of the operations we do on trees tend to be logarithmic. Logarithmic is great. Notice it's the next one after constant, right? Logarithm is great. Okay? Linear is the one we just talked about. Linear is not terrible. I mean, if you have to do a linear algorithm, well, it means you're going to have to go through all the elements whenever you want to do something. And we have a data structure that we've already done with that. Which one was that one? Linked list. Linked list. If you want to insert into a linked list at the end and you don't have a tail pointer, you got to walk all the way through the linked list, right, to get there. Okay, that's a linear operation. Okay, that's why another reason linked lists are not particularly fast. Okay, quadratic and polynomial. These ones we'll talk about in a little more detail in a few minutes, but it basically means that there's some sort of squared amount of things you have to do. Like you have to do a value, and then you have to do that same value again for a squared number of times. Okay, polynomial is the same thing. It could be like cubic or like raised to the third power, fourth power, or something like that. Okay, exponential is an interesting one. We don't see too many data structures that have exponential behavior because it's really terrible. All right, I mean, if you design an exponential function, remember the Fibonacci function? Remember how terrible we said that was? That's an exponential function. We don't want those kind of functions if we can help it, right? I will show you an example of an exponential function. I think it's on the, yeah, here we go. Anybody ever played the Tower of Hanoi puzzle? I don't know if you played it before, yeah? You might have seen it. Let me put this down. When you, what you do is you have this board with three like columns or pegs on them. And then you've got all these disks, okay? And the disks go onto the pegs, but you're trying to get the disks from one peg all the way to like the third peg. And what happens is you can only move one at a time, and you can never put a larger one onto a smaller one. Okay? So watch how this would do it. I totally screwed this up in class earlier today. Okay, this is just for the three. We want to get these ones over to this one, and we can't actually move a bigger one onto a smaller one. You can only move one at a time. Okay? So for instance, anybody know how this is going to work? Am I screwing this up again? No, that one's good, right? OK, so we put that one there, and then we put this one here, and then we put this one back over here, because we want a blue one to be all the way over here. And so we move the blue one over here, and then we move this one back over here, and then this one goes on to here, and that one goes on to there, and we're done. Okay, and that actually took 7 moves, okay, to do that. All right. I'm not going to try to do the next one because I'm terrible at this game. This is frustrating. A friend of mine had this as a kid, and it frustrated me to no end. I never had the patience for it. Test for ADD or something, I guess. But anyway, so let's take a look at 4, right? Well, the nice thing about this little flash animation here is that it will actually solve it for you, right? So watch what happens here, OK? So I mean, hey, I mean, I guess I could go to it, but it's gonna do it, right? And it's a little bit more tricky now because you've only got 3 things to deal with. You have to actually figure out, hey, now I got to move that one there, and then finally I get the bottom one on there, right? But I have to do each individual stack gets moved over to the other side each time, and then we're done. Okay? And that took 15 moves. Okay, more than 7 moves. It took 15 total moves, right? You want me to try another one? You can do all the way up to 8. You want me to do 8? No? I'll do 8. But the nice thing about 8 is, yeah, you can actually fast forward on this. So any guesses on how many steps 8's going to take? What is it? 2 to the 8th minus 1. Ah, very good. So 2 to the 8th is 256. You think it's going to take 255 moves? Yes. I think that's a good answer. Anybody else have a different answer? No? Let's try it. So it's got to drop them all on here again. I would if you had given me 8 as a kid, I would have just been like, psh, where's something else to do, right? Fast forward, boom, right? It goes nice and fast, this one. Okay, but take a look what's going on. It's got to, boy, it takes a while because it's got to move individual pieces into the middle one every time, and it has to do it one at a time, right? So it's getting there. right? Sorry, what did you said how many? 255? 2 to the 8th minus 1. OK, that's 255. Yeah. We're getting there. OK, so 170, 180, getting there. And, oh, we might make it. I know. So that, and we're done. And how many did it take? 255. Woohoo! All right. So it is an exponential algorithm. And in fact, there's no better way to do this, right, than this exponential algorithm, which means that it takes 2 to the however many elements you have each time. So if you try to do 64 here, forget it, right? 2 to the 64 minus 1 is like way too big, right? I mean, 2 to the 32 minus, if you did just 32, right? That's actually 4 billion moves, right? And you don't want to do that. I can guarantee you that. And the computer doesn't either, by the way. Won't want to do that either. But that's an example of an algorithm that is exponential. Okay, and we don't like those ones. If we can help it, we don't like them. We can try to avoid them. Okay. All right, so back to our dirty little trick again. If we wanted to take this and find out the order of it, even though that looks scary, right? By the way, there's one other one that I missed. I didn't put in the table before. Actually, let's go back for one sec. This one, there's one that's n log n. Okay? N log n algorithms are interesting. We will see them when we get to sorting. There's sorting algorithms that are n log n. And where would n log n fit into this picture? Okay, you're multiplying n times the logarithm of n. Yeah? Yeah. After linear. Yeah, it's bigger than log n, of course, log n times n. And it's bigger than log n, so it fits in right here. Okay? So it's actually it's a relatively slow one, but not super slow. But in some cases, it's the best you can do is n log n. Okay? All right, back to this. If we want to take a look at the big O notation of this function, well, what do? The first thing you do, get rid of the constants. Sometimes you can't get rid of the constants. And they're like corner cases, kind of like our corner cases that we'll talk about. I won't give you anything where you have to worry about that. But if this number was like 10 to the 100 or something like that, then you're kind of in trouble, right? I mean, you've got until you get 10 to the 100 and more values in there, then you're going to be bound by the fact that that's a 10 to the 100, right? Which is called what, by the way? 10 to the 100. A googol. Not spelled the same way. It's a G-O-O-G-O-L, googol. Yeah. And then there's a 10 to the, no, sorry. What is it? A Google to the Google? Is that what it is? Is that the next biggest one? Which is called a Googleplex, right? Do you know what Google, the company, calls their headquarters? The Googleplex. Right? Which kind of clever, you know. Google's a clever company. Just, you know, we have to deal with that. So anyway, so in this case, you throw out the constants, right? Then you start looking at which one's going to overwhelm all the others. Well, look, the 5 is not going to overwhelm anything, right? You do 5 things being not to overwhelm. The n log n thing will not overwhelm the n cubed business, right? Because n cubed is going to expand is going to get bigger much faster than n log n. And so therefore, we just say this is big O of n cubed. That's it. Pretty straightforward. This is not this stuff tends to confuse people. There's lots of other pieces to the big O notation that we are not going to cover in here. If you take algorithms class, you might get into some of that. But we're going to kind of talk about big picture stuff here. Okay? Questions on that? All right. Let's look at nested loops. Okay? If you take a look at this loop here, this is a really simple loop. It just says I'm going to input a number n, and the result, we're going to get the result. We're going to set the result equal to 0. And then we are going to, for every value of n, we're going to go through 2 loops. We're going to go through one loop and then a nested inside loop also going to n. Both of them are going to go to n. And we're going to add the result there, and then we're going to return that result. Okay? Let's look at the analysis of this. The inner loop is just a complexity of n, because you're going through n times that inner loop. Right? The outer loop, also a complexity of n, like you go through the outer loop n times, but because the inner loop is inside of it, you're going to end up doing the result operation n squared number of times. Okay, so the total complexity of this is order of n on the order of n squared, which is called quadratic complexity. Not such a good thing. It's kind of slow. Okay, and it turns out that some types of things we try to do with computers end up being n squared complexity. Okay, the big one that everybody always talks about is talking about graphics on your computer, right? Your computer has pixels. The whole screen is a square of pixels, right? And if you want to touch every one of those pixels, you've got to go, if you had a square monitor, n times this way through all the pixels, and then n times down through all the pixels, meaning you have to do n squared operations to affect all of those pixels on your screen, right? This is why companies like NVIDIA and AMD make lots of money off GPUs. Right? They make lots of money off graphical processing units because they have figured out better ways to handle this n squared complexity. How do they do it? Any ideas how they do it? They still have to do this, but they do it in a kind of a fancy way. Any ideas? They throw more hardware at it. What they do is they say, hey, if one processor had to do n squared calculations, that's going to be pretty slow. What if we had n squared processors? Right? Or what if we had, in this case, n being some fixed number that they can actually build onto a chip, like some of them have 512 processors on one chip. Right? Each processor, not particularly fast. Like it doesn't do much. But each processor can do stuff like tell if a pixel next to a pixel needs to be shaded differently because it's the colors, the lighting scheme is on it or whatever. So what they do is they take these many processors and they parallelize the problem, and they end up doing this pretty quickly. Right? They still have an order n squared algorithm, but they do it by lots and lots of processors. Kind of cool. We can also look at triply nested loops. Right? This is where you've got I, j, and k. Same exact idea, right? You've got 3 levels of nesting here. Well, 2 levels of nesting. And the total complexity here is n cubed. Anybody think of a n cubed type of problem? Off the top of your head? Anybody have a 3D television? Yeah, if you have a 3D, I don't think those are even catching on, but 3 dimensions, right? I mean, we live in a 3-dimensional world, x, y, and z, right? Or x, y, z, whatever, right? And you live in this 3-dimensional world. Well, if you're going to do calculations in a 3-dimensional world, you're going to end up with a lot of these order n cubed or cubic kinds of algorithms. Not very fun. Okay, that's still like a hard thing to deal with. Okay, don't get me started with n to the 4th. You don't want those. Okay. All right. So that's how nested loops work. Okay. Let's look at let's see. We did nested loops. Let's look at searching. Now this is actually kind of what we did earlier. Oh, before I even go into that, let me show you a little bit about. Let me just show you some of the. Let's see. I have the asymptotic analysis nested loops. And I think what I do is, if I recall, I hit like I do how many I want to actually do there. OK. So I just said what this is doing is this is actually going through the loop, and it's doing that calculation. And it's just taking some time. Well, this is the Unix tip of the day, right? There's a time function, which you can use to actually run your program. And we did this before already. But you can run your program, and it can actually time how long it takes. And in this case, that takes 6,000ths of a second, 6 milliseconds. That's really fast, right? Because it doesn't take a computer long to do 1,000 times 1,000 iterations of something, right? 1,000,000 times through something. It doesn't actually take that long. I've got a really fast computer, right? Not to mention the fact that I actually had to slow this down. I had to cheat a little bit. So if you look at the code online, you'll see a line in there that's like, I think I might have even put cheating. Right? To slow this down so this time thing works. My computer is just too fast, and I didn't want to get into like bigger integer types and things to do this. It's just too fast. It's nice. But if you do, let's say 10,000, let's see how long that takes. Time asymptotic analysis nest 10,000. OK, that takes 0.192 seconds, right? And that is actually 100 times bigger, right? Calculation. It's, let's see, 10,000 by 10,000, right? So it's 100 times bigger, and it takes 1.192. So if it's 100 times bigger, right, it should take 10,000 times longer. Is that what it is? Let's see if I'm getting this right. I'm forgetting if the algorithm would do it that way. If the input size, no, sorry, the input size is only 10 times bigger in this, but we're doing a quadratic equation, so it's going to be 100 times slower. So if I was taking to do this for, instead of 10,000, I was to do it for 100,000, which is 10 times bigger, it should take about 100 times longer than this, right? 100 times longer than 0.19 seconds is about 19 seconds or so, right? So we got to wait around a little bit for this one to end. Okay, and it's still cranking along, cranking along, cranking along. There we go. About 18.5 seconds, about 19 seconds to do this. Okay, so it's on the order of n squared. And if we tried to do 10 more, right, it would be 100 times more. And I'm not waiting 1,800 seconds for this, right, to stop. If I do 10 times more, it's going to be 100 times slower. 10 times more and 100 times slower because it's an n squared, and it's going to take 1,800 seconds. Make sense? Seeing some people going, no. The n squared algorithm. If you look at the n cubed algorithm, right? I think that's the n, hang on. Let's see, it is, yeah. The n cubed algorithm I don't know if I even had to slow this one down. Yes, I guess I did. For 1,000, it takes 1.87 seconds, right? For 10,000, that's 10 times more. It's going to take 10 times 10 times 10, or 1,000 times. I'm not waiting around for it, right? Because it's going to be really, really, really slow in this case. Okay, so that's the. I stopped it. It didn't actually finish. Okay, but here's what the searching is doing. Okay, that was the nested algorithms. Now let's talk about the searching. So in the searching one, lots of code here. Unfortunately, this is a C++ thing. You've got lots of code to do something that's relatively simple. Okay. Here's what we're trying to do. We are just trying to search through that array up there, that way up there. Search through the array. I'm passing in the array and the length and the number to find. And all it's doing, this is a sorted array, by the way. Okay. So the array goes from 0 all the way up to 1 million, but all the integers are sorted in the meantime. And so what I'm going to do is I'm going to go through this, and I'm going to first say, it's in a loop from 0 to the array length. And it's going to say, is the answer in the array what I'm looking for? And if it is, we're done, and we return true. If it's not, okay, what do? We have to check. If it's not, we check if the array is actually greater than the number. If the array value is greater than the number we're looking for, that means we actually skipped the number we're looking for, and it's not in the array. Does that make sense? Okay? Maybe not. It is a sorted array. Okay, it's a sorted array. But we're just doing what's called a linear search on this. There's a reason it's called linear search, right? Okay, and then that's all this is doing. What is the best case in this scenario? If we're doing a linear search, and we're going through the values, and we're looking for values, what's the best case scenario? Dylan? First one we check is done. And so we've got a time of like 1, right? However long it takes to go through that number of loop, we're done. That's the best case. What's the worst case? Yeah. If the ones we're looking for in the end, which is how many things do we have to look through? All n of them. Which means that this is big O of what? Big O of n. Okay, the worst case is the one we care about. This is a linear one. It's big O of n. Not too bad, but not amazing. We talked about this other kind of search earlier. Even looks like more code, right? We talked about this other kind of search called a binary search. Okay, and a binary search is the one where you start in the middle, and then if your number that you're looking for if the number in the array is greater than the one you're looking for, okay, then you go to I guess in your case, it's going to be this side of the array. You're going to go to the lower part of the array. And then the same thing. And you keep chopping the problem in half each time. When we chop the problem in half, okay, and here's the chopping in half part, right? When we chop the problem in half, okay, half and half and half and half and half, that is what kind of asymptotic notation? Like what do we get out of that? What behavior do we get? Any ideas? I heard it. Logarithmic, right? The nice thing is if you're chopping parts into halves, half and then half and then half and then half again, you get logarithmic behavior, which is great because that's one of the really fast ones. Okay? So if you look at the two types of output we've got here, okay? If you look at the one problem with this one was that, let's see, hang on, here it is. Let's see, it's analysis search 1. The problem with this one is that I had to create a giant array of like 1 billion integers. It takes like 5 seconds just to create that array and populate it, all right, on my computer. So what's going to happen is, oops, you know what? I want to time this. So time. There's another. Bang, bang means do the last thing, except tack on the time part. So it took about 4 seconds to do this. And what I did was I searched for 1,000, which is really early in the array. And it took 1,001 comparisons to do that. And it spit out the array. Now, let's try. I don't even know if 10,000 is going to give us much benefit here. Remember, it takes about this much time to actually populate it. It actually might be a little bit less because of the caching effects here. Was it? No, it was close. Just a little bit more, right? Just a little bit more than that. So we haven't even started to tap the resources here. The resources are being tapped just populating that array. Let's try 100,000 and see if that makes a difference. Yeah, it did. OK. So now we got to 100,000, which was 6 seconds. So it was about 2 seconds, 6.7, about 2 seconds faster than, or slower than the 10 times less. So now we should be able to say it takes about 2 seconds to do that. If we do 10 times more, it's a linear search. This should be 10 times slower, meaning we should be about 20 seconds plus the original 5, about 25 seconds or so to do this. We'll see. To search for 1 million out of that billion. I guess I didn't need to go all the way to 1 billion. But to do the search now, this should take roughly, what about 24 seconds? Did we say 24? Something like that. 24, 25 seconds. Yeah. What's that? This is the linear search. Yes. This is the one that's just searching straight through and taking its time going through each one and checking. And I didn't have to cheat on this one. And there you go, 26 seconds. There you go. OK? So if we did 10 times more, it would take about, let's see, 10 times more than the 24 seconds. So 240 seconds. We're taking about 10 times more time to search all the way to the billion. Question?
Wait, so why didn't it take 60 seconds?
OK, yeah. So good question. So there's overhead. Remember so this is actually a good point. Those integer parts that we did before, like the parts that we're ignoring, that's the overhead part in some cases. In this case, the overhead, it takes about 5 seconds to create that array, no matter how many elements you have. So you have one element that you're searching for. If it's right at the beginning, or if you're only searching for one, it's right at the beginning, right? It will take the 5 seconds anyway. And then if you're searching for the millionth or whatever, it'll take 5 seconds plus the whatever it takes to do that other search. So that's the difference there. OK, if we look at the binary search, right? We do the binary analysis. Let's see. What is it called here? Search binary. And let's say we look for 100,000 straight off the bat. Again, takes about 5 seconds to create this array. Okay? And then what it's doing is it's actually printing out all the different comparisons it's doing. At first, it compares between 0 and basically 1 billion. And then it says, oh, I'm less than half of that. So I go and do 0 to 500 million. And then I'm less than half of that, 0 to 250 million, blah, blah, blah. And it goes down and does this, this guess my number sort of search in the middle thing. And this took about 4.41 seconds. So it took, in this case, I might have had fewer elements in this one. But anyway, let's say we look for the millionth element. Well, what are you going to expect the time's going to be about? About the same, right? Because it's a logarithmic search, and we haven't actually made it to the next logarithm, right? So it took about the same amount of time, right? So logarithmic searching is really fast. Binary searching is really fast. You're chopping the problem in half, half, half. The maximum number of steps you have to do is the log of the total number of elements. And logs get big very, very slowly. Okay, so that's the way we can approach the problem. Okay, all right. Let's go back here and talk a little bit more about numbers. If you look at a program, and it has 1,000 elements in it, and the logarithmic solution takes 10 nanoseconds. Okay? Basically, you're doing log base 2 of 1,000. Takes 10 nanoseconds, right? Then that's really fast, by the way. Right? 10 nanoseconds is like super duper fast. A nanosecond is 1 billionth of a second. So that would be 10 billionths of a second, really fast. It would take the linear algorithm 1 microsecond, also very fast, right? 1 millionth of a second. It would take the quadratic approach a millisecond, still pretty fast. You're not going to worry about a millisecond going by. And then the polynomial, in this case the cubic solution, is 1 second. All right, you might notice 1 second. You won't notice any of the other ones. You'll notice 1 second. But still, not too terrible. Anyone guesses on the exponential solution? How long that would take? 100 seconds? Good guess. Anybody else? It does depend on n. It's 1,000. Oh, it depends on a. OK, so let's say a is 2. Yeah, 2 what? Yeah, a is 2. And what do you think? Other guesses? 2 to the 10,000? 2 to the 1,000? Yeah. Turns out that it's 10 to the 284 years. All right? Remember, we're talking about exponential growth. Exponential growth is really, really fast. Okay? Exponential growth is not something you want to do. If you could choose between the logarithmic and the exponential, right? Every single time you pick the logarithmic. Otherwise, you'll just end up at the heat death of the universe before your problem ends, right? Okay. So let's. By the way, this is if you. These are all pretty fast except for the last one, right? But if you had it so that instead of 10 nanoseconds, it took the logarithmic 10 milliseconds, 1,000 times slower. It takes your linear 1 second. You must start noticing that. It takes your quadratic 17 minutes. It takes your cubic one 694 hours. And yeah, this one just keeps going, and you will never see the end of that one. OK, I mean, that's just the way it goes. OK, so you don't want the exponential. Luckily, there aren't that many exponential ones that we need to worry too much about. There are some. And in fact, if you find some, I mean, there are some that we have to deal with. And there's methods for getting partial solutions and things. But you don't really want to have to deal with that. Questions? OK. Summary, quick summary. If you are doing constant time, that is not going to be dependent on your input size, which is great. You love that. Holy grail. If you're doing linear, at each step and you reduce the problem by a constant value, like 1 or 2 or 3 or whatever, that's still going to be linear, order linear, a big O of n. Logarithmic, cut the problem in half or a third or some value where every time you're making it 1 something smaller. Right? 1/2 or 1/3 smaller. That's logarithmic. Quadratic, doubly nested things. Cubic, triply nested things. Exponential is interesting. You are reducing the problem, but you're reducing the problem into 2 or more problems of a smaller size. That's what the Towers of Hanoi was doing. It's reducing the problem into smaller problems, but making multiple of those smaller problems, which is the only way you can solve that one. OK? All right. Any other questions? All right, I'll see you guys Monday.